Okay, so today I want to go over double replacement reactions and combustion. So I'm first going to go over double replacement, and then I want to show you a demonstration of that. So in a double replacement reaction, what you will see are two compounds forming two new compounds. So what's happening here is the ions, and you could think of it either as the cations or the anions, are switching places. So it's kind of like a square dance. So they switch partners. So you can, when you're done, the cation of one compound is going to be combined with the anion of the other. So here we start with AB and CD. The B and D switch places, or the anions are switching places. A ends up with D, C ends up with B. Okay, so I'm going to first show you an example of a double replacement reaction, and then we're going to go over the reaction that you saw occur. Okay, so what we have in this video is we're gonna watch the experiment that the reaction that occurs between lead 2 nitrate and potassium iodide. The left-hand Erlenmeyer flask, if you look at that closely, you're gonna see the solution is a pale yellow, and that's our potassium iodide in solution. The right-hand Erlenmeyer flask in the video is actually a solution of lead 2 nitrate. The middle Erlenmeyer flask is empty right now, and what the scientists are going to do is they're going to add the solutions of potassium iodide and lead 2 nitrate to that middle Erlenmeyer flask, and you're going to see the very rapid formation of lead 2 iodide. So watch this. Okay, and that is our lead 2 iodide. And if you look at it, it looks very similar to paint. And a lot of lead compounds used to be used to make paint because they make very bright colors. Obviously, lead, though, is as a neurotoxin, so that's why we don't use lead in paints anymore. Okay, so let's look at the reaction that you just saw. And what we started with was a solution of lead 2 nitrate. So since this was dissolved in water, we would say it's AQ, which stands for aqueous. And then potassium iodide. This was also dissolved in water, would also be AQ. So in this reaction, you could think of it as either the lead and the potassium are switching places, or the nitrate and the iodide. So it doesn't matter which one. But the important thing is you should end up with two new compounds. So we end up with potassium nitrate, and we could figure out the formula of this because we know that potassium has a +1 charge, nitrate has -1 charge. We also know that lead starts with a +2 charge, and then iodine has a -1 charge. So our other compound for our product would be the lead 2 iodide. So those are our products. And we'll go over in a future class, like how you would figure out which of those, if those were aqueous or so on, using something called our solubility table. Okay, so when you're figuring out the products for a double replacement reaction, think about the charges of each of your ions, and remember that you can think of either the cations are switching places or the anions are switching places. Okay, so I want to go over the last type of reaction now, which is combustion. So in a combustion reaction, you have a burning of any substance in oxygen to produce heat and light. The most common type of combustion reaction is a hydrocarbon, which just contains carbon and hydrogen, and sometimes oxygen. And this is reacting with oxygen and producing carbon dioxide and water. This would be a complete combustion reaction. However, you can have incomplete combustion when you don't have as much oxygen present. This can happen with furnaces or with cars, And here you could have the hydrocarbon reacting with oxygen, but also producing some carbon monoxide. Let's go over one more type of combustion reaction, and this would be combustion of a metal. And this essentially would be like rusting, metal rusting. So one of these might be if you had combustion of magnesium. This would be just magnesium reacting with oxygen and then forming magnesium oxide. And remember, this is also like a synthesis reaction with oxygen, but if you see combustion of a metal, this is what it's talking about. You do not have carbon, you do not have hydrogen, so you cannot be producing carbon dioxide and water vapor. So you're just going to be producing the metal oxide. So if though you have some kind of hydrocarbon, like CH4, if it says combustion of that, that would be adding that to oxygen. And then the products there would always be carbon dioxide and water. But like I said, in reality, sometimes we have incomplete combustion where you can get some carbon monoxide instead. Okay, so for metals, you form the oxide. For hydrocarbon, you produce carbon dioxide and water vapor. Okay, so I'm going to now show you the whoosh bottle demonstration. This is actually going to be the burning of ethanol in this case to produce carbon dioxide and water. So watch this.
Exactly. All right, take it away, Carl. So we've got a 5-gallon jug, water jug. It's completely dry and empty. We're going to add to it a little bit of ethyl alcohol. Okay? Now this is 95% ethyl alcohol, so it is very, very concentrated, if you will. All right. It's also very flammable. Jay, what I'd like you to do is pick that jug up and sort of swish that liquid around. So what we want to do is generate some vapors inside the jug. And if you can, carefully tip it almost on its side and rotate it. But don't let any of the liquid come out. That's perfect. Sure. We want to coat the inside. We're going to build up lots of vapor because that's what we want to ignite. We're going to show you how flammable some vapors can actually be. So tip it totally upright. A little bit of liquid comes out. Let it drip for a second. Perfect. Go ahead and upright it. Take this away. And now we've got a very flammable mixture of gas inside there. I'm going to give you some matches. Okay. You've got a pair of tongs for safety. Okay, so let's light the matches here. And once you get them lit, give them a second. And then we're going to have you come over the top of the jug and just drop the matches into that flammable mixture of gases. Right, here we go. 3, 2, 1. Woo! Yeah. It ignited. You get that whoosh of air coming out. That's what we call the whoosh jug. Yes, yes. And then the air expands and some of it gets pulled back in. And then there was a secondary sort of whoosh as it sort of oscillated back and forth. Okay. Now, the other thing that happened there that's kind of subtle, we're going to do it one more time, is that when the combustion happens, the gases inside warm up and they expand. And that's what caused that jet of flame to come shooting out. Now, the question is, what would happen if you could contain those gases inside the jug while they cool? Okay, so we're going to do the same thing again. Jay, I'm going to let you go ahead and grab your tongs. We'll do the same deal. And this time we'll add a little twist at the end. So I'll let you go ahead and put your matches in there. We're going to get them lit. And then we'll drop these into our flammable mixture. Same way. Let them burn for a couple seconds here. And, okay, I think we're ready. Go ahead and drop it in. Here we go. 3, 2, 1. Okay, we've got some nice oscillation there. And now if we cap this, as that air begins to cool, it takes up less space. And you can see that slight imbalance in air pressure is allowing atmospheric pressure, 14.7 pounds per square inch, to start to crush the jug. You might even see something similar to this if you rinse out your milk jugs before you recycle and put the cap back on. Warm water will do the same sort of thing. No flames involved, so it's a nice, safe way you could do this at home. But isn't that amazing? A little bit of warm air. Wow. Let the pressure back in, it pops right back.